In this video, we're going to talk about one final technique that's used to take the derivative of potentially complicated expressions, and this technique is called logarithmic differentiation. This concludes the chapter on techniques of integration, and in the final chapter of this class, we will be looking at a variety of real-world applications of calculus. Very exciting. So today's section is called logarithmic differentiation, which, as the name suggests, is concerned with logarithms, and we're going to begin by reviewing some of the properties of logarithmic functions. And then we're going to use logarithmic differentiation, and what this helps us to do is find the derivative of functions that look like this: a function of x in the base and a function of x in the exponent as well. To set the stage for why we might need this technique of logarithmic differentiation, let's consider the following two exercises. In scenario number 1, we're finding the derivative of e to the power sine of x. So our base in this case is constant. Our base is the constant number e, and the exponent is a non-constant function of x, sine of x. So this is a prime opportunity to use chain rule, and in particular the chain rule shortcut formula that we studied when we specifically had e to the something. The derivative of e to the something was copy-paste e to the something and multiply by the derivative of that something. In this case, cosine is the derivative of sine. Likewise, chain rule was what helped us to find the derivative of quantities such as cosine of x to the power 2. This is sort of the opposite situation compared to the previous exercise. Back then, our base was constant and our exponent was a function. This time, our base is a function and our exponent is a constant. In this case, we can still use chain rule, but this time we're taking the derivative of outer function is the power function, square. Inner function is cosine. Now the derivative of the outer function is 2 times blank. And if we put the inner function inside, it will become 2 times cos. Then we multiply that by the derivative of cosine. The derivative of cosine is minus sine. So once again, we would use chain rule in the case where our base was a function, but our exponent was constant. But what do we do in a situation where neither the base nor the exponent is constant? For example, what if we had cosine x below and sine of x on top? To answer that question, we're going to look to the logarithm, which had some very unique properties. For example, if you took the log base b of a quantity called a multiplied by a quantity called c, then a product inside of the logarithm became a sum outside of the logarithm. So if you look at PEMDAS, for example, the log transformed a product, a multiplication inside, to an addition outside. If you take log base b of a divided by c, then this became log base b of a minus log base b of c. So in terms of PEMDAS, this took an internal division and turned it into an external subtraction. And interestingly, if you take the logarithm of a to the power c, then the exponent of c on the inside can be turned into a constant multiple on the outside. So the logarithm, in terms of PEMDAS, could take exponents and turn them into multiplication. Now these rules do work with any base, but we're going to focus on the case of log base e, the natural logarithm, everybody's favorite logarithm. And let's consider what would happen if we simplified a quantity like we saw on the previous page. What if we take the natural log of cosine to the power sine? In that case, the exponent sine x can be brought down to the front and turned into a constant multiple. So this can be turned into sine x times the natural log of cosine x. Now notice that this is now a quantity that we can differentiate. We can take the derivative of this. We can take the derivative of this by first using product rule to split up the sine times the natural log, and then using chain rule to figure out natural log of cosine of x. So that's the idea. If you're trying to find the derivative of something like function to the power function, you apply the natural logarithm to take that exponent and turn it into a constant multiple. To turn it into something that you can differentiate using just the product and chain rules. So just as before, I'm going to outline the general technique, and then we're going to do several examples showing what that technique looks like in practice. So the first thing that you want to do is apply the natural log to both sides. And simplify using the log properties. Now once that's done, what you will have is an implicit relationship between y and x. So what you can do then is apply implicit differentiation. To the equation in step 1. And then, if the question calls for it, you may need to rewrite the quantity called dy dx as f prime. So to demonstrate the technique, let's go back to this running example where we're asked to find the derivative of f of x equals cosine to the power sine. Now, for simplicity's sake, I'm just going to go and rewrite f of x as the single quantity y. And then I'm going to go ahead and apply the natural logarithm to both sides of this equation. So natural log of cosine of x to the power sine x. Now, on the right-hand side, we know that natural log of cosine to the power sine can be simplified by taking that exponent and turning it into a constant multiple. So now we have the natural log of y equals sine of x times the natural log of cosine of x. That concludes step 1. We've applied natural log to both sides and we've simplified using the logarithmic properties. Next, let's go ahead and let's implicitly differentiate both sides of this equation. Let's take the derivative with respect to x of both sides of this equation. Now on the left side, we have an opportunity to use the chain rule. We have our outer function, which is given by the natural log of blank, and the derivative of outer would then be 1 over blank. Our inner function is y, and the derivative of inner is what we call dy dx. 1 divided by 1 over blank, which is now 1 over y, times dy dx. And then product rule applies here on the right side. The first function times the derivative of the second function, natural log of cos, plus natural log of cos times the derivative of sine. Now once again, to find the derivative of natural log of something, we can use chain rule, where the outer function is natural log and the inner function, in this case, is cosine. And following the same chain rule reasoning, the derivative of this first term would be 1 over cos times the derivative of cos, which is negative sine. And in the second line, we have natural log of cos times cosine. Natural log of cosine times regular cosine. Okay, so far so good. So let's put those two parts of the equation together. And then what would dy dx be? Dy dx would be equal to this entire expression on the right multiplied by y to get rid of this 1 over y. Here is one sort of aesthetic conventional difference between implicit differentiation problems and these kinds of problems. In this case, our original question actually gave an explicit formula: y is equal to cosine to the power sine. So we didn't start the problem with an implicit relationship, we sort of created an implicit relationship. Because of that, the preference is to give our final answer in terms of x's alone, to not allow this y here. So our preference is to replace that y with what we know it equals to. Y we know is equal to cosine to the power sine. So a bit of a monstrosity here, but this is really the only way that it is possible to manually find the derivative of something like function to the power function, is to apply natural log to both sides and then use implicit differentiation to find the value of dy dx. Now the work in the previous exercise, I think, demonstrates the fact that it can be convenient to have a shortcut formula for the derivative of natural log of something. For example, in the previous exercise, we had to deal with that situation twice. Here on the left-hand side, we had the derivative of natural log of y, and we also had it right here, the derivative of natural log of cos. So rather than having to go through the full shenanigans of chain rule every single time, it can be nice to have a shortcut formula similar to the shortcut that we have for the natural exponential. So let's go ahead and give a shortcut formula for the derivative of the natural log of some function. In this case, we can use chain rule, where the outer function is the natural log of blank, and therefore the derivative of the outer function is 1 divided by blank. The inner function, of course, is g of x, whatever it happens to be in your particular problem. And we call the derivative of g prime. So then what would my answer be to this question? My answer would be 1 over g of x fills the blank, and multiply that by g prime of x. Or in simpler terms, if you want the derivative of natural log of a thing, first reciprocate g of x, and then put g prime of x in the numerator. This is the shortcut formula for the derivative of the natural log of some quantity, usually some quantity other than just x. Let's see if we can apply that to the following example. Here we're asked to find the equation of the tangent line to f of x equals x squared plus 1 to the power x at the location where x is equal to 1. Now, in order to stand any chance of answering this question, the first thing that I need to do is find f prime, because f prime is what's going to tell me the slope of the line. So step 1, let's find f prime. Now in this case, we have function of x, and the power is also a function of x. So this is a prime opportunity to use logarithmic differentiation. I'm going to replace f of x with y for short, and then I'm going to apply the natural log to both sides. And properties of logarithms say that you can take that x and change it so that it's a constant multiple, or rather just a multiple outside of the natural logarithm. And we get x times the natural log of x squared plus 1. So now let's apply implicit differentiation. Let's calculate the derivative with respect to x on both sides. Now on the left side, we can go ahead and we can use the shortcut formula for the derivative of natural log of something. The derivative of natural log of something is equal to 1 over that something multiplied by the derivative of that something. Whoops, I made a typo here, folks. This is supposed to be saying d dx. Because now let's use product rule to split apart this expression on the right side. We have the first times the derivative of the second, plus the second times the derivative of the first, and once again, working on simplifying the right side of the equation, we have an opportunity to use the shortcut formula for the derivative of natural log of x squared plus 1. That would be equal to x squared plus 1 in the denominator and the derivative 2x in the numerator. Meanwhile, we have natural log of x squared plus 1 times the derivative of x, which is just 1. So dy dx, the slope of the tangent line, would be equal to y times this entire expression on the right-hand side. 2x squared divided by x squared plus 1 plus the natural log of x squared plus 1. And in these problems, since we start the problem given y explicitly in terms of x, Our convention is to go backward and say, let's not use y, let's use x squared plus 1 to the x instead. Okay, this problem is still just getting started. What we have found so far is a formula for the derivative at any location. If I wanted to, instead of dy dx, I could rewrite this as f prime of x. But I still need to scroll back up and remind myself that this is not what I'm trying to find in this problem. In this problem, I'm trying to find the equation of the tangent line to the function where x is equal to 1. So step 2, we need to actually answer the question. We need to find the tangent line. To that end, let's go ahead and let's find the slope at the given x value of x equals 1. In other words, let's find f prime at 1. What that means is we're going to have to go into this giant formula, and everywhere there was an x, now we need to put a 1 in. Okay, so x squared plus 1 becomes 1 squared plus 1. To the power x becomes to the power 1. Here we have 2x squared, so that's 2, 1 squared, so that's 2. That was divided by 1 squared plus 1, 1 plus 1. And over here we have the natural log of 1 squared plus 1. Now if I simplify that, 1 plus 1 to the first power is just 2. 2 divided by 2 is just 1. And then add that to the natural log of 2. So this would be the slope of the tangent line at x is equal to 1. Next, we need to find the point on the tangent line. We know that the x is equal to 1. Now we need to figure out the y value. The y value is given by the output of the original function. So the y value is equal to 1 squared plus 1 to the power 1. The y value is equal to 2. So the point on the tangent line is the point 1, 2. Okay, so let's go ahead and let's use this slope and use this point to finally finish the problem and get the equation of the tangent line. The tangent line's equation is going to be y minus the y of the given point equals this entire hefty slope here. So 2, 1 plus natural log of 2, multiplied by x minus the x of the given point. Now this function is sufficiently strange that I think it is worth just verifying graphically that this answer is correct. So in blue, we have the graph of our given function, which is x squared plus 1 to the power x, which is this really sort of interesting behavior. It looks almost like an exponential function, except for this strange little wiggle close to the origin. I went ahead and typed in the equation of the tangent line that we found, y minus 2 equals giant slope times x minus 1, and sure enough, that pink line is perfectly tangent to the graph of the function. Now this video is probably already too long, but I really did want to show you one more really neat example of how the idea of logarithmic differentiation can be used to help to find derivatives of complicated functions. To date, the only log property that we have actually used was the last one in our list. What happens if you take the log of something with an exponent? But there were two other properties of logs which involved products and quotients. So one of the things that logarithmic differentiation can do is give us a way to calculate the derivative of something that might involve a particularly complicated quotient or product. Instead of having to use this giant, ugly, recursive quotient rule, product rule mess, another way that can be simpler sometimes is to use logarithmic differentiation. So let's see an example of that here. Let's find the derivative of this monstrosity. So the first thing that I'm going to do is apply natural log to both sides, using y as a stand-in for f of x. So the properties of logs say that a product inside the log gets demoted to a sum outside the log. And a quotient inside the log gets demoted to a difference. So this quantity here can be rewritten as the natural log of x squared plus 1 plus the natural log of 5x minus 2 minus the natural log of e to the x. And as a matter of fact, the natural log of e to the x can be simplified much further because natural log and e cancel out. So this is just equal to x. So natural log turned a product slash quotient into a sum slash difference. And so instead of using the nasty product and quotient rules, now we can use the much more pleasant sum and difference rules. Let's combine the sum and difference rules with the shortcut formulas that we have for the natural log of something. On the left side, we get 1 over y times the derivative of y. Then we have 1 over x squared plus 1 times the derivative of x squared plus 1. Then we have 1 over 5x minus 2 times the derivative of 5x minus 2. And finally, we minus the derivative of x, and that's just equal to 1. So all that's left to do really is to clean this up. A lot of writing, that's for sure, but no more calculations. So this would be the derivative of the function given to us in this problem, found using logarithmic differentiation. We didn't have to use quotient rule at any point, and we didn't really have to use product rule at any point, because log properties allowed us to split that product slash quotient into a sum slash difference. So that creates a problem which, although perhaps just as tedious as it was before, is much easier than it was before, and you have far less opportunity to make calculus or arithmetic mistakes. Okay, that concludes today's material. Today we talked about logarithmic differentiation, which is a differentiation technique that exploits the properties of the logarithm. It's used, for example, to calculate the derivative of function to the power function, or, as in this case, to calculate the derivative of an extremely complicated product slash quotient.